right, as we get ready for your test coming up in the next lesson, I want to take some time to review. And about a third of the test, okay, so one of the 3 pages of the test is going to be exact values of special angles that are in whatever quadrant they happen to fall into. So let's do a little practice with that as we look at page 65 in your textbooks. Page 65, number 17, asks us to find the value of the cosine of 210 degrees times the cotangent of 300 degrees plus the secant squared of 240 degrees plus the sine of 330 degrees. Without using a calculator, of course. So just take them one thing at a time, right? Start with the cosine of 210, and you always start by asking yourself which quadrant we're in, and it's quadrant 3. Slightly bigger than 180. The reference angle, 30 degrees away from 180, and we know that the cosine of 30 degrees, may want to draw those special triangles there on your paper. What's the cosine of 30 degrees? Since you'll have to do that on the test tomorrow. Cosine of 30 is square root of 3 over 2. But ASTC, quadrant 3, cosine is negative. So there's our first value. Now we go to the next thing. No noises, thank you. Cotangent 300 degrees. We start by asking ourselves which? Quadrant 4, right? Reference angle? 60. The cotangent of 60 degrees.
X over 2, or 1 over 2, 1 over square root of 3 over 3.
Square root of 3 over 3. But quadrant 4, class? Negative. Square root of 3 over 3. Plus, now we come down, this is secant squared. Let's hold off on the squared for now. Let's just find the secant of 240, then we'll square it. Question? Right, we're done. Quadrant class. 3, reference angle. 60. 60 degrees away from the 180. And what is the secant of 60?
1 over square root, so 1 over
hypotenuse over adjacent.
1 over 2.
Hypotenuse over adjacent.
Square root of 3 over 3. 2 over 1. 2.
Square root of 2 over 1. Oh, or just square root of, or 2 over square, 2 times square root of 3 over 2.
It's just 2.
That's what I just said.
Right?
I said 1 over 2. Oh, 2 over 1.
2 over 1. There we go. Okay? Hypotenuse over adjacent. 2 over 1. And then, of course, we're going to square the 2 over 1. And we're going to add the sine of 330. Quadrant 4. Reference angle 30. Sine of 30. 1 over 2. ASTC, quadrant 4, sine is negative. By the way, I didn't do ASTC here. Quadrant 3 secant is negative, but it doesn't really matter because it's squared. But I guess as a formality, since we're reviewing, we probably should address it. So here we've got to multiply these two things. We've got to raise this to a power, and then we'll have all additions. So let's start by multiplying. Negative square root of 3 over 2 times negative square root of 3 over 3 is going to give us what?
3 over 6.
Positive 3 over 6. Square root of 3 times square root of 3 square root of 9, which is 3. 2 times 3 is 6, and negative times negative is positive. Of course, we could reduce this to just get 1 half. Plus, of course, negative 2 when you square it gives you a 4. And we've got plus negative a half. We could just say negative a half. Obviously, we see here the half and the negative half. It's just 4. Cancel. And so if you had taken the time to plug all this into your calculator, you would have gotten 4. Just a nice, easy, rational value. It would take too long with the cotangents and the secants and all of that, so for sake of time, we won't. Though, if you want to go back and watch the video and do it on your calculator, you can. Number 19, we've got 5 times the sine of 5 pi over 6 times the tangent of 5 pi over 4 plus 10 times the cosine squared, pay attention to that, of 5 pi over 3. First thing we always start with is quadrant, 5/6. Second quadrant, reference angle when we see denominator 6. 30. And sine of 30. 1 half. Quadrant 2, sine is? Positive. And we're going to multiply that by a 5. We're also going to multiply it by whatever this is. Well, 5/4 puts you in quadrant 3, reference angle. 45. Anytime it's a denominator 4, change it to 45. I like to think in terms of degrees, not radians, which is why I'm doing that. But pi over 6 technically, yes, is the reference angle. But then you have to go the next step of, well, what's pi over 6? Or what's pi over 4? So, but change it to 45. 1. And in quadrant 3, tangent is positive. All right, plus, we're going to do 10 times whatever this is squared. Quadrant.
3. 2. Wait, yeah, it's 3.
4. Because 3/3, 5/3 is bigger, but it's nearly 6/3. So it actually puts it in quadrant 4, reference angle 60. Anytime there's that denominator 3, cosine of 60. Adjacent over hypotenuse. Adjacent over hypotenuse. Adjacent over hypotenuse. 1/2. People, look at the triangle and think. All right, and quadrant 4 cosine is. Not that it matters because it's going to be squared anyway, right? So 1/2 when you square it gives you
2.
1.
No, 2.
1/4. You square the 1, square the 2, you get 1/4. So this is 10 over 1 times 1/4. And over here we've got 5 over 1 times 1 over 2 times 1 over 1. So we've got this multiplication. Order of operation says we do that before we add 5 over 2.
5 over, that's just 5.
And then here we get,
10 over 4.
which reduces to
5 over 2.
5 over 2. So we have 5 halves plus 5 halves equals 10 halves, which is just 5. And so the whole thing just comes out to 5. Now, if you were to try to enter this on your calculator, and we can because it's sine, cosine, tangents. This one's going to be a lot easier to enter. With secants and cotangents and reciprocals, it's a mess. But here's the problem. You're going to have to enter radians. So let me show you something real quick on your calculator. You won't have to do this on the test, but I'm going to show you anyway. If you look at the top of your calculator, you will see a button labeled DRG. Now, you probably won't. Ethan, yours is going to be here in the setup. And see here you have degrees, radians, gradients. That's the same thing as DRG, degrees, radians, gradients. So you'll just want to hit the number 4. All right? For the rest of you, if you look at the top of your screen, you see DEG at the very top of the screen. But if you hit the DRG button, it changes and says rad for radians. Now that it's in radian mode, I want you to do this. 5 times pi divided by 6 equals, and then for you guys, you just hit the sign button. Ethan, you'll do sign of answer. And it comes out to 0.5. Well, we could write that down. If it were a crazy decimal, we could put it in the memory, right? And then we could do, let's see, 5 times pi divided by 4 equals, and hit 10. Of course, it comes out to 1, but if it came out to a crazy decimal, we could put that in the memory. And then we could do the one that's on the calculator times the 0.5 that was here times 5 equals. And it gives all of this to be a 2.5. Then we come over here. 5 times pi divided by 3 equals, hit the cosine, which of course comes out to 1/2, and then hit this x squared button. And it comes to 0.25 times 10 gives you 2.5. You could then add this 2.5 to the other 2.5 to get 5. So again, the calculator can handle radians just fine. Now, hit the DRG button twice to go back to degree mode. Ethan, in your case, do the setup and go back to degree mode, because in the test tomorrow, you're going to want degrees, okay? The radians are going to throw you off if you have it in radian mode. Gradients?
What is that?
Gradients is an engineering method of measuring angles. We won't use it in this class.
Will we use it in any class?
Not in high school, no. In college, if you go into engineering, so hit the 3 button, and that should give you a D. And again, you should have seen an R a moment ago for radians. All right? We'll do a little bit more with the radian mode on the calculator later, but for now, we'll just stick with the degree mode. Number 21, go ahead and copy it down onto your paper. Number 21, copy it down onto your paper. Got the cosecant of negative pi thirds times the cotangent of 330 degrees plus the cosine of negative 3 pi over 4 times the cosecant of 45.
When you see
degrees.
4, you think 60, and when you think 3, you think 45, right?
Nope. Denominator 3 is 60, denominator 4 is 45, denominator 6 is 30. All right, first thing I notice, I got some negative angles here. That's no good, right? So we got to add 2 pi. In this case, when I add 2 pi, what do I make it look like?
5 pi over 3.
6 pi over 3, which when I add it gives me
5 pi over 3.
5 pi over 3 times the cotangent of 330 plus, here we're going to add 8 pi over 4, 2 pi, but it's 8 pi over 4 to get cosine of
5 pi over
5 pi over 4 times the cosecant of 45 degrees. All right, here we go. Quadrant, reference angle, 60, and cosecant of 60. Yeah.
2.
1 over 2.
2 times the square root of 3 over 3.
I was looking at 30.
Make sure you look at the correct angle. And then quadrant 4 cosecant is negative. So negative 2 square root of 3 over 3. All right, let's go to the cotangent 330. Quadrant
4.
4. Reference angle from 360.
30.
30. Cotangent of 30.
Square root of 3 over 4.
Square root of 3 over 1. And because we have a fraction here, I'm going to go ahead and leave it over 1. I think that'll help us. And then quadrant 4 cotangent is negative. All right, quadrant 3. Reference angle
45.
45. Anytime you see that denominator 4, cosine 45. Square root of 2 over 2. But quadrant 3 cosine is negative. Times. Hey, this is quadrant 1. We just cosecant 45. Go to your 45, 45, 90 triangle. What's the cosecant? Square root of 2 over 1. And in quadrant 1, everything's positive, so of course, it's positive. All right, here, negative times negative, class. Positive. Square root of 3 times square root of 3.
12.
Square root of 9, which is 3 times 2,
6.
divided by 3, 2. And then over here, we have plus a negative times positive. Well, negative times positive is going to be negative, so it's plus a negative. All right, square root of 2 times square root of 2.
2.
Square root of 4, which is 2, divided by 2,
1.
1. And
But
so
it's
2
gonna be
minus 1
negative.
is 1. And so this whole thing
Is this
equals
something
1.
new? Because I don't remember ever doing this, like in class. Did you ever like? It's just adding a bunch of them together. It's just, like,
Yeah, all we're doing is, the main step is this right here.
So it's not worthy.
No,
of
this is
all
just
of
showing you how we could, do some math with these things. But the main thing is, can you get these ratios?
it. So what's the real life application to this stuff? Like, if you're in a field
Thinking
of,
skills, processing,
So-
tackling a problem that looks challenging and process at a time, knocking out piece at a time, consistently, meticulously, without making any errors.
So I guess
So you don't get
also-
fired from your job.
I guess also like, what job would you use this in? Like,
Thinking
architecture?
skills, any job.
Oh, I mean, no, like these, like cosine. kind of thing.
And maybe engineering. It's all about thinking skills. I've told you that for years. Math is about thinking skills. I don't care if you ever use cosecant again in your life, but if you know how to think, then you're going to be way ahead of the competition. All right, I want you to drop down to number 23. Speaking of thinking, looking at number 23, he says the tangent of theta is negative square root of 3 over 3. And the question is, for what values of theta is this true? When is tangent square root of 3 over 3? Well, we've done something similar to this before. Tangent's what over what, class? Opposite over adjacent. What triangle has an opposite of square root of 3 and an adjacent of 3? None. But we know that square root of 3 over 3 is really just a rationalized form of 1 over square root of 3, or rather, negative 1 over square root of 3, correct? Okay, so it begs the question, when is the opposite 1 and the adjacent square root of 3?
60-degree angle and 1 square root of 3 and 2.
Careful.
30-degree angle.
The 30-degree angle has an
What did I
opposite
say?
of 1. You said 60.
No.
Opposite of 1 is the 30-degree angle. So I know that this is going to be a 30-degree reference angle. But theta may not be 30 degrees. In fact, I know it's not because tangent is negative. ASTC, where is tangent negative, class?
That's 2 and 4.
Second and fourth quadrants. So what angle in the second quadrant has a 30-degree reference angle? 150 is 30 away from the 180, right? So theta could be 150 degrees. What in the fourth quadrant has a reference angle of 30 degrees?
330.
330. So apparently theta could be either 150 or 330 in this problem. Do you see kind of reverse thinking? It's the same thing we were doing, but backwards. Let's put this next one in reverse. We have the cosecant of theta is negative 2 times the square root of 3 over 3. Well, again, that's rationalized. What's the original ratio?
2 over square root of 3.
Negative 2 over square root of 3. All right, and cosecant's what over what? Hypotenuse over opposite. So, when is the hypotenuse 2 and the opposite square root of 3? For what angle? A 60 degree angle. That's my reference angle. That may not be theta. In fact, I know it's not theta because cosecant is negative. And ASTC, when is cosecant negative, class?
3 and 4.
3 and 4. So what angles in quadrants 3 and 4 have reference angles of 60 degrees? Well, in quadrant 3,
120.
quadrant 3, come down 60 beyond the 180, 240. And in quadrant 4, come down 60 from the 360, 300. So apparently theta could be either 240 degrees or 300 degrees. Look at number 27. It says the cosine of theta is a half. Well, what is cosine? 1 over what?
Adjacent over opposite.
All right, for what angle is the adjacent 1 and the hypotenuse 2?
45.
Yeah,
60 degrees. Oh, I was just seeing if you change your answer when you heard something different. Good, way to stick by your gun. 60 degrees, right? That's the reference angle. But ASTC, when is cosine positive? 1 and 4. So what quadrant 1 angle has a reference angle of 60?
30 angles? No,
60. Remember, in the first quadrant, reference angle is the angle. So 60 really is an answer here. But what about in the fourth quadrant? 300 degrees.
That's a big margin, a big ratio.
It's either 60 or 300, so 2 possible answers. I want you to do 22, 24, 26. 22, 24, 26.
Negative.
Let's go and take a look at these together. Number 22. Number 22, when is the sine of theta square root of 3 over 2? Ethan? What were your two answers?
Oh, okay. I was confused for a second. 60 degrees.
60 degrees or?
130 degrees.
Class
Right.
120. 120 degrees. Comes 60 up from 180 gives 120. All right, number 24. When is the secant square root of, or negative square root of 2? Jamie?
45 degrees and 225.
You're right about the 225, but not 45. Because when is secant negative? Not in quadrant 1. 45 would be in quadrant 1. Chris?
I had 45 and 315, so I was in there.
Well, it'd be positive in 1 and 4, but that was a negative. So we've got to have quadrants 2 and 3, Quentin.
134.
And,
234.
right,
Or
225. Yeah, 135 and 225.
Wait, what?
Should have been the answers there for 24. Let's go back to Jamie on number 26. The cotangent is 1. When is that going to be true?
Quadrants 1 and 3.
So,
It's 45 and 225.
good. 45 degrees to 25 degrees. Did we get some of those right?
Yeah, I did.
All right, questions. Does it make sense now at
I
least?
got the first two right.
All right. And again, that's just giving you some more practice with the special triangles, that we're going to be using that skill in a few more chapters. But you won't have something quite like that on the test. I do want you to practice number 20, though, there at your seats. Do number 20 at your seats, giving you some practice finding exact values of special angles. Then we'll do a calculation with it. We won't actually do the calculations on the test, but we will need to find exact values of trig ratios. Of special angles, excuse me. Trig ratios of special angles.
I have a question. So
Yes.
could you like go through and find all the quadrants first and then go back and find all the...
Yeah, you could go through and find all the quadrants, then you could go through and find all the reference angles, then you could go through and find all the ratios, then go through and do all the ASTC. You don't have to do them one at a time necessarily. Good question.
So I have a question.
Yeah.
I got the reference angles. What do we do?
You find the tangent of 40, you find the secant of, well, that wouldn't be 55, but you would actually find, using a special angle, find the tangent of that angle, find the cosecant of that angle, find the cosine of that angle, and so forth. And the only reason we don't do that with the given angle is you can't fit the given angles into triangles, so that's why you need the reference angle. But once you got it, you can go from there.
Cosecant is adjacent over opposite, right?
Sorry?
Cosecant is adjacent over opposite, right?
Gotta memorize these tricks. This is the first thing we talked about all year.
Sin.
All right, for sake of time, pencils down. Let's take a look at these together. Number 20, we should have found quadrant 3, reference angle 45, tangent of 45 is 1, and quadrant 3 is positive. For the next one, we should have found, again, quadrant 3, reference angle 45, and the cosecant of 45 is negative square root of 2, negative because of ASTC in the third quadrant. Then we're going to add in, let's see, we've got a quadrant 2, reference angle 60, cosine of 60 is a half, and that's going to be negative 1/2. And then we had the cotangent 210, of course that's quadrant 3, reference angle 30, cotangent of 30 is the square root of 3, and that's going to be positive square root of 3. So far, so good. All right, questions? All right, then we just multiply 1 times negative square root of 2 is negative square root of 2, and then negative 1/2 times square root of 3 is negative square root of 3 over 2. And they don't combine. If you wanted to try to combine them into a single fraction, you could get a common denominator of 2, right? And that give you negative 2 square root of 2, negative square root of 3 all over 2. You can factor out the negative, slide the negative out front, but I mean, that's as much as you can do. It doesn't come out to a nice, easy number. But again, the main thing is getting these ratios. Okay, questions on that?
Could you use negative square root of 2 minus square root of 3?
You could just leave it like that, honestly. But again, you're not going to have something quite like that on the test, but you will have to be able to do this, 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 this for an entire page on the test. And you're going to be able to do that.
How many problems are on the test?
You'll find out. All right, so let's go ahead and take a look now at reviewing some other things we talked about. Of course, we said that an angle, when placed on the Cartesian plane, needs to be placed in a particular way. What do we call the way an angle should be placed? We call this standard position of an angle. 2 key factors. 2 things must be true for an angle to be in standard position. No, not necessarily.
Angle on the x-axis.
One side. Which side? The initial side of the angle must be on the positive x-axis. Initial side on the positive x-axis. What else must be true? The vertex must be at the origin. The vertex must be at the origin. Of course, the terminal side can end wherever it ends, right? If it happens to end at 90, 180, 360, 270, something like that, we call it a quadrantal angle. But again, anywhere else, it's just, quadrant 1 angle, quadrant 2 angle, so forth. If an angle happens to rotate clockwise, we would describe that angle as being?
Well, negative.
Negative. Clockwise rotation would be negative rotation. Counterclockwise, of course, would be positive. And of course, it's possible for multiple angles to share the same ending side, right? One angle could go this far, the other angle could go all the way around and then end at the same point, or an angle could go backwards and end at the same point. So those angles would be called angles that share the same ending side. Coterminal angles. Coterminal angles. And of course, to find coterminal angles, really easy. All you do is
Plus or minus 360.
add or subtract 360 degrees to find coterminal angles. We talked about another measure for angles besides degrees, and that is, of course, radians. And how many radians are in one complete revolution?
2 pi.
2 pi's are in one complete revolution. And so therefore, a single pi would be how many degrees? 180 degrees. And we use that fact to convert from degrees to radians. So if I had 75 degrees and I wanted to convert it into radians, what would I do, class? Multiply by pi over 180. Pi over 180 degrees. To get the degrees to cancel away, you could also maybe reduce by 5 to get like 15 and 36. Oh, we're going to reduce by more. I could maybe take out a 3 from each of these and get 5 and 12. And so we'd say it's 5 pi over 12 radians, right? It would be easier on your calculator to do 75 fraction bar 180 and let it reduce it to 5/12 for you, right? But, you know, we could do it by hand as well. What if I had radians? Maybe I had 3 pi over 8 radians, and I want to convert that into degree. Well, I'd use probably degree symbol, but I want to convert it to degrees, class.
3 times pi divided by
180 over 5.
Multiply by 180 degrees over pi. That'll allow the pi's to cancel. We could also cancel, well, you know what, just multiply 180 times 3 and divide the 8 out. Otherwise, I guess I could divide by
67.5.
67.5 degrees. Or 67.5 degrees, or 67 degrees 30 minutes if you wanted to be a nerd. Don't be a nerd. Questions on converting degrees, radians, degrees, all that stuff. Of course, we know 90 degrees is how many radians?
Pi over 2.
Pi over 2. That's going to be useful for finding complementary angles, won't it, in terms of co-functions and things we'll look at here in a moment. 270 degrees, how many radians?
3 pi over 4.
All right, it's 3 90s in a row, right? So if pi over 2 is, or 90, then 3 pi over 2 would be 270. That's good to know for, you know, finding your quadrants and stuff like that. We said if the cotangent of an angle, we'll call it phi, is 15 to 8, and if I knew that the sine of phi is less than 0, what would the cosine of phi be equal to at your seats? Find it. The cotangent of phi is 15 to 8, and the sine of phi is less than 0. Find the cosine of phi. We had this on a quiz, this kind of problem on a quiz not too long ago.
So it's going to be negative.
Yes, you should have figured out quadrant 3. So cosine is going to be a negative ratio.
15 over 17.
Negative 15.
And then you'll find the hypotenuse to be 17. Adjacent over hypotenuse gives negative 15 to 17. Okay, let's do one more of these. Suppose we had the secant of gamma is, let's say, 10 to 9. And I know that the tangent of gamma is greater than 0. And I want to find the cosecant of gamma.
Square root of 19 over 10.
So you should have found quadrant 1, which will give you a positive.
The secant is opposite over adjacent.
Uh-oh. Hypotenuse over adjacent.
So I said,
It's an opposite over adjacent.
I don't have hypotenuse over adjacent. I put hypotenuse over adjacent when I was working out. And I still got square root because you have to do Pythagorean theorem and you get
100 square root of 19 over 19.
There we go. We should end up with 10 over square root of 19, which becomes 10 times the square root of 19 over 19 for our answer. All right, questions on this one?
No.
Slow it down and think on the test tomorrow, right? Slow it down, put in the thoughts. You do a great job. Don't rush through and get some wrong answers because of it.
I know the sign now though.
Let's suppose we have the sine of 3 pi over 10, and I wanted to rewrite this as the co-function. Well, to find a co-function, first of all, class, we need to, well, just change to the co-function of sine.
Cosine.
Cosine, but we also need to change the angle to its
No.
complementary angle. Co-function, co-angle. Co means complementary. So we've changed to cosine, but the complementary angle, how do I find a complement?
Minus from pi over 2.
Pi over 2.
Pi over 2 minus. 90 minus normally, but we'll say 3, or pi over 2 minus here. Common denominator, of course, is 10. So if we got a denominator of 10, we'd be multiplying top and bottom by 5 to get 5 pi over 10, so we get 2 pi over 10, which reduces to pi over 5. Supposing we had, though, the tangent of negative 310 degrees. No. What do we need to do? Plus 360 to get tangent of 50. Okay, that's more like it. Now we can rewrite in terms of the cofunction. Change tangent to cotangent, and then for the angle, co-angle, complementary.
40.
90 minus to get 40 degrees. So the cotangent of 40 degrees. But what if I had something like this? The cosine of 98 degrees. Well, you can't take the complement of 98.
Take the supplement.
Nope. That's not what we do for cofunctions. It's always a complement.
Minus 90.
No? Okay,
No.
folks. Let me talk, please, instead of interrupting. If it falls outside the first quadrant, we're going to have to reduce it to an acute angle, so we can do 90 minus, right? So we're going to have to reduce this down. What quadrant?
Quadrant 2.
2. And the reference angle in quadrant 2, measuring from the 180, is 82 degrees. ASTC in quadrant 2 cosine is?
Negative.
So we're going to rewrite it, first of all, as negative cosine of 82 degrees. Then we can change it to the cofunction. But when we change to the cofunction, what do I do with this SIGN right here? Just keep it. Cosine will turn into sine, and now I can do 90 minus to get 8 degrees. How about this one at your seats? Supposing we had the secant of 512 degrees. Ooh, thoughts?
Minus 360.
Minus 360. To get the secant of? Again, can we do 90 minus? No. So we have to reduce this down to the same function of a positive acute angle. Get a reference angle. We'll say quadrant, reference angle.
38.
28, get careful on the borrowing there. 28 degrees. And ASTC secant in quadrant 2 is?
Negative.
So we get the negative secant of 28 degrees. That's a horrible 2. Once we've got it this way, now we can change to the cofunction. And what will we get for our answer?
Cosecant of 62.
Negative cosecant 62 degrees. Questions on that? What about if we had radians here? Let's suppose we had the cosine of 9 pi over 5.
Minus 5 2.
Well, we don't subtract pi over 2, we would subtract from pi over 2. But this is too big to subtract from pi over 2.
Subtract.
So we have to get it down to a reference angle.
Pi over 5.
Well, is it? What quadrant?
Quadrant 4.
Start with the quadrant. Now, quadrant 4, that's 360, but we're thinking 2 pi or 10 pi over 5. So what is the reference angle, Ethan?
Pi over 5.
It is pi over 5. And so how do we rewrite the cosine of 9 pi over 5?
Negative sine over, negative sine.
Not yet. Just rewrite it. ASTC,
Positive.
keep the cosine for now. We're about to change it, but for now, keep it, and then keep the reference angle. Reducing to the same function of the positive acute angle. Now, let's turn it into the cofunction. So class,
Keep the sign.
positive, sine, and here we subtract from the pi over 2.
Yeah.
Need a common denominator, and we get
Negative.
3 pi.
3 pi over 10. Right? 5 pi over 10 minus 2 pi over 10 gives 3 pi over 10. And there would be our answer. Okay? Questions on that? Reduce to same function first, then change to the cofunction. Back in chapter 3, we had 5 equations that you need to have memorized for tomorrow. One of them is to find the length of an arc. And we need to understand that anytime there's a curved path and you're asked for a distance along a curved path, that's arc length. Our formula for arc length, S equals, anyone remember? R theta rad. S equals R theta rad. You multiply the radius times the angle of rotation to get the arc length, but the angle must be in radians. We had an equation for the speed at which an object moves along an arc path. Call that linear velocity equation.
equals theta rad.
How about V equals S over T? The arc length, which is the distance traveled, divided by time. But if we put those first two equations together, we could also get V equals R theta rad over T, where we could plug the R theta rad in for the S. We said that there's two ways to calculate the speed of an object as it moves in a circular pattern. If we're looking simply at the distance along the curved path, that would be linear velocity, or the speed rather along an arc path, that would be the linear velocity. But if we're trying to see how much of an angle is translated along a unit time, that would be angular velocity, represented by the Greek letter omega, a lowercase omega, looks like a W with maybe a little bit more curvature on the ends of it. And omega equals
TW?
not distance over time, but angle over time. Theta rad over T. But we could kind of see how this equation and this equation could blend together. And if we were to replace the theta rad over T with the omega, we could also say that linear speed, feet per second, meters per second, would be equal to R times omega. A couple of things to emphasize here. V would need to be in either meters per second or feet per second. Of course, the theta rad needs to be in terms of radians. Time will be in seconds. But if you're finding an arc length or finding a radius or something like that, you could use whatever unit happened to be provided. Questions on this? Make sure you know those formulas, able to use those tomorrow as well. You can go back in your book and look at countless examples that you could use there. That's pretty much the test. Okay? Main thing, the biggest thing, a third of the points. Can you find the sine, cosine, tangent, secant, cosecant, or cotangent of special angles, even if they're outside the first quadrant? Beyond that, we've got a little of this, we've got a little of the cofunction stuff, we've got a little bit of the degrees, radians.
The majority of the points are going to come from what we did most of the time.
But a third of the points is from what we were just working on. Basically that massive chart, except you got to do it working it out instead of memorize, because nobody wants to memorize a massive chart. There's no written homework this evening, and you'll be dismissed. Have a wonderful rest of your day.